Have you ever stopped to think about what the single most important invention of the last century really is? I'm not talking about the computer or the internet or even the smartphone. I'm talking about the tiny, invisible component that makes all of them possible. Today, we're going to unlock the secret heart of all modern electronics, the PN Junction. I mean, just think about it for a second. There is one fundamental piece of tech behind the brilliant light of an LED, the clean energy from a solar panel, and literally the trillions of calculations happening inside the device you're watching this on right now. It all comes back to this one single microscopic secret. So that's the big question, isn't it? How can one simple little structure, just a boundary between two types of material, be the absolute foundation for so much of our world? Well, that's exactly what we're here to break down. To get to the bottom of it, we're going on a quick tour. First, we'll meet the PN junction itself. Then we'll see how it creates this special depletion layer. We'll understand its built-in electrical barrier, unlock its superpower as a one-way gate, and finally, we'll connect it all back to the tech that shapes our everyday lives. All right, first stop, let's meet the main character of our story. So what are we really looking at here? Well, at its core, a PN junction is made from a single piece of stuff, usually silicon. You start with what's called P-type silicon, and then, using a process like ion implantation, you basically change the top layer into N-type silicon. And that boundary, right where the two types meet, that is the PN junction. And you might be wondering, what do P and N even stand for? Well, it's pretty simple. P is for positive, because that side has a bunch of positive charge carriers. You can think of them as tiny, empty parking spots for electrons, which we call holes. And N, you guessed it, is for negative, because that side has a ton of extra free-moving negative charges, our old friends, the electrons. The junction is just the border where these two opposite worlds collide. Now, here's where it gets really interesting. The moment that border is formed, something happens. It doesn't just sit there. An amazing new thing is created, something called the depletion layer. It all happens in a flash, really. First, the materials are joined. Immediately, all those free electrons on the N side see the empty holes on the P side and just rush across the border to fill them up. But here's the magic trick. When an electron leaves the N side, it leaves behind an atom that's now positively charged, an ion. And when it fills a hole on the P side, it makes that atom negatively charged. These ions are stuck in place, and they create this permanent barrier zone right at the junction. And this explains the name perfectly. It's called the depletion layer because it's been depleted of any free-moving charges. It's a neutral, stable, no man's land, and it is the source of all the junction's power. So this depletion layer, this little zone, does something pretty incredible. It creates its own internal, permanent voltage. Let's take a look at how that works. Remember those positive and negative ions we were just talking about, the ones that are locked in place? Well, anytime you have a separation of positive and negative charges, you automatically create an electric field between them. It's just basic physics. And because those ions are fixed, this electric field is permanent. It's always there. This permanent electric field creates a natural voltage difference across that junction. Now, physicists have a name for this, of course. They call it the built-in potential. It's just an inherent property always there, even when there's no battery or power source connected to it. And this isn't some abstract theoretical idea. It has a real, measurable value. For your typical silicon junction, the kind that's in pretty much everything, this built-in potential is right around 0.9 volts. So, the easiest way to picture it is like this. The PN junction basically has its own tiny internal battery. It's constantly creating this little voltage barrier that pushes back against any more charges that try to cross. And that barrier, that's the key to everything. Because once you have that barrier, you can control it. And that control is what turns the PN junction into probably the most important electrical component ever created, a one-way gate for current. This graph here is called an IV curve. And you can think of it as the PN junction's superhero pose. It shows you the current, that's the I, versus the voltage, the V. And as you can see, something really dramatic happens. If you push voltage in one direction, almost nothing gets through. But if you push in the other direction, once you overcome that little built-in barrier, current just flows like crazy. This is called biasing. If you hook up a battery that pushes with the natural flow against that internal barrier, well, that's called forward bias. You overcome the barrier, the gate swings open, and current flows. But if you hook up the battery the other way around, in reverse bias, you just make that internal barrier even stronger. The gate slams shut, and pretty much nothing can get through. And this superpower, this incredible ability to act as a one-way valve for electricity, it's got a name: rectification. It's the fundamental property that lets us control electricity in all sorts of complex and amazing ways. Okay, so how does this simple one-way gate end up building our entire modern world? Let's connect the dots. When engineers are designing circuits, they use that simple arrow symbol on the left to represent this whole physical process we've just talked about. And the arrow literally points in the one direction that current is allowed to flow. This component, the PN junction, has a simpler name. It's called a diode. So let's bring it all back home. A solar cell? It uses that built-in electric field to grab electrons that get knocked loose by sunlight, forcing them to flow in one direction, as current. An LED? That's just a special kind of diode that releases energy as light when current flows through it the right way. And a transistor, the building block of all computers, is basically two of these junctions put back to back, creating a switch you can flip with electricity. So from light to energy to information, it all comes down to this one elegant, simple one-way gate. And that kind of leaves us with a final thought, right? If this one simple principle is behind everything we have today, what new technologies become possible tomorrow as we master building these things at an even more incredible scale?